Greetings, students. Mr. back with you again today. We're going to continue on. The last completed was a short one over Q reaction quotient and its relationship to K, the equilibrium. I said that accompanying assignment, which was the equilibrium assignment, was, and so we're continuing on today. Continue on with our next lesson over LeChatelier's principle, which is honestly probably one of the most important principles. The most used out in industry today. So let me today's notes. Didn't mean to do that. Sorry about that. There we go. So, just picking up right where we left off with Q versus K. So, in writing this process, from hydrogen and nitrogen gases, the German chemist Fritz Haber sought the factors that might be varied to increase the yield of NH3. Let me go back on Fritz Haber. He might be a guy, if you're interested in wanting to Google or look up on the internet, he is quite famous. He won the Nobel Prize in 1918 in chemistry for his work with ammonia. I recall that 1918 also interestingly enough, end of World War I. Haber played an extremely important role for the German government in World War I. Ammonia has several important uses. The main one, I should say, is in that ammonia is the main ingredient in fertilizer. Without the ability to mass produce ammonia, there is no way a crop would be what they the to mass ammonia on a very large scale that led us out of areas where lots of very farms, whereby farmers just grew crops for basically themselves, their own family, and local community. Now to a level of our crop yields are so much higher that even with fewer farms, we are able to produce not only grains to communities, but to export billions and billions of dollars of grain each year. Without the ability to mass produce ammonia or fertilizer, would not have happened. Another important use of ammonia is in the production of nitric acid, which is used in the production of explosives. So it is in that regard Haber, played an important role in the German government during World War I. In fact, not only in the production of explosives, but he was also able to synthesize a process of the government, chlorine gas, which is a common name of mustard gas. And if you guys know or remember anything about World War I, the Germans introduced mustard gas as a chemical during that war. World War I was called the war, where the battles went on in the trenches. Basically, one side dug a trench here, another side dug a trench here, and they would fire ammunition back and forth. Mustard gas is very, very, like I said, it's chlorine gas, and if you inhale it, basically what happens is the moisture or water in your lungs and airways reacts with that chlorine gas to produce hydrogen, which is extremely corrosive. It will burn the linings of your trachea and your lungs, and in fact, will produce acid, suffocate, or you will drown. Very and horrible way to die, and Fritz Haber was very much involved with that. A little historical side there, top. In regards to ammonia, like I said, without him, we're not where we are today to agriculture. So anyway, we back in the very beginning of this unit when we talked about KP, actually calculated the KP for production of ammonia, nitrogen, and hydrogen gases, and in fact, that value of KP is very, very small. I think it's somewhere on the line of 4 times 10 to the minus third. All right, that's a pretty small number. So what that means is equilibrium quantity of product, which is ammonia, versus the quantity of the reactants, nitrogen and hydrogen, is very small. So as the equilibrium is set up, it's not very conducive to producing large amounts of ammonia, which obviously we need to do. However, very temperature and total pressure of the system, remember it's a closed system, based on a principle put forward by the French chemist Henri LeChatelier. If a system at equilibrium is disturbed by a change in pressure of one of the components, then the system will shift its equilibrium so as to counteract the effect of the disturbance. This is known as LeChatelier's principle. LeChatelier's principle is any equal process. All right, and so it forms very many equilibrium reactions that are key to remaining alive. For instance, water content. So we talked about osmosis. It moves in and out of the cells because the cells have to be hydrated. Remember, our bodies are about 70% water. Our cells have to be hydrated to a proper level in order for certain bioprocesses within our body to work correctly. And so basically what that says is if our bodies are stressed by they do not have enough to become dehydrated, the natural reaction to that and so and that's an equilibrium process involving LeChatelier's principle. The body is stressed by a lack of water. The brain tells you drink. All right. Another one, temperature. Our bodies are set to run properly around 30 degrees Celsius, 98.6 Fahrenheit. When our temperature goes up, if we get all right, then the stress to the body, our body is too hot. When your body gets too hot, it starts pushing 100 degrees, 105 degrees Fahrenheit. It's going to cause some serious problems. All right, and so react to an increased temperature. It begins to shiver, which helps release heat from the body. It increases the surface area. You get boost surface area of your skin so that more rapidly and be lost from the because it blows from warm to cooler environments. And so that's another natural biochemical process involving this principle. So let's look at changes in product or reactant concentration. The shift will be in the direction that minimizes and reduces the effect of stress. All right. So if more is added, whether it be or product, the reaction will shift to consume that reaction is added. Then the reaction is going to shift to the right where the products are, make more product additional reaction. So if more of a substance is added, the reaction will shift to basically what that means is the net effect of that is shift to the opposite side. Right? If you add reactant, which is on the left, it will shift to the right to form more product. If you add more product, which is on the right, it will shift to the left to make more reactant. All right. Removal of a substance results in shift to more substance. All right. So the same thing. So if you take the stress is now there's not enough of it, so shift in order to make more will then negate the effect, decrease the effect of the stress of a substance then shifting to reduction of that substance, which then means an effect of that is it will shift to the same side. Again, we're going to look at some specific better. Number two, for changes affecting volume and the resulting pressure change. Okay, this is now Boyle's law. Now, remember, volume and pressure are inversely proportional. If a system's at equilibrium and its volume is decreased, in other words, it's taken from one container and put into a smaller one, then the pressure increases. Boyle's law tells us that. And according to LeChatelier's system, by shifting equilibrium and reduce, we put a equilibrium reaction mixture in a smaller container whereby the volume is smaller, pressure in that container increases. So stress is high. What we want to do is reduce the pressure can reduce by lowering the number of moles of gas. All right, lowering the number of moles of gas. So in the direction in which there are a fewer number of moles, check about that. If its volume increases, if its volume is decreased, then its total pressure increases, which means the stress is the pressure is too high. All right, and so the reaction is going in order to reduce the pressure. All right. So if the pressure is too high, all right, then it's going to shift. It's going to shift to the side with less moles, whichever side that may be. That would then decrease the pressure. That's Avogadro's law. Remember, moles and pressure are directly. If you lower the moles, the pressure is going to go down. And if the pressure is too high, that's what you want to do. All right. Next page. So conversely of that, The stress, the reaction is too cold to relieve the stress. We want to produce more heat. All right. Now, this particular reaction was exothermic. Where was heat found? Heat was on the right side. If we produce more heat, we want to shift it to the right. Now, if that was an endothermic heat had been over here, and we want to produce more heat, we would have shifted it that way. All right. But in an exothermic reaction, which this one was, we want to shift to make more product. We want to make more heat. And so in this particular reaction, shift to the right. All right. And then finally, this kind of puts everything together now. If you were asked how to maximize the amount of sulfur trioxide produced, then what suggestions would you make? Exactly what Fritz Haber was doing when he was trying to increase that he could make from a reaction whose K was at standard conditions very, very small. K is small, so we have a reaction in various ways, and K get okay. That's what we're asking. So SO3 was a product, all right. So we want anything possible that would shift the reaction to the right. All right, we wanted to make more product. So as we look back at our list here, what we do to make this to the right, all right, four to shift to the right. Well, the first thing that was listed in letter A was add oxygen. You add more reactant, it's going to use it up. Product, shift right. It didn't say anything about SO2, but SO2 is a reactant as well. We could add more SO2, the other reactant, and that would shift the product to the right as well. Letter F. Remove product. It would cause a product, which is what we want to do. So remove SO3. That would do it. Remember, when the temperature was too high, the reaction shifted to use up the heat. Since the reaction was exothermic, that would have shifted it to the left. If we cool the reaction down to cold, reaction's going to try to make more heat since this is exothermic. So lower the temp. All right, cool the thing down. And then we have done volume 1. All right, well, up here, if we had taken the reaction and put it in a larger volume container, we would have action to the left. The pressure in a larger container, the pressure was too low. It would have shifted to the side with more moles, which was the left side. Well, what about the opposite? All right. So if we reduce the volume, the reaction in a much larger container, why not run it in a small one? All right. Then it's going to increase the pressure, and so now the reaction is going to react to that stress by going to the side with fewer moles, which would lower the pressure, and the side with fewer moles for this particular reaction was the right side. So all of these things was the reaction shift right would increase the value of K, which would cause reduction of more SO3. And like I said, this is exactly the principle that Fritz maximize the amount produced in the that action. Again, without that possibility of doing those things, then there's no way we could be able to mass produce ammonia that we do each and every year. So, LeChatelier's principle, remember it. It is a big one. All right, it is extremely in the application of equilibrium to industry today. All right, so that concludes our lesson today. Respond to your assignment number 7, LeChatelier's principle, and so hopefully this helps explain how that works. Like I said, it's an extremely important application of equilibrium in every area to many different industries. And it's equally important to us as our bodies are a closed system. And many of the biochemical reactions that sustain and keep us are based on LeChatelier's principle. So this is Mr. Keister signing off again. Until lesson, everybody take care, and I'll see you soon. Everybody.